Hi, and welcome back. In the previous video, we built a bare-bones reactive programming system and used it to implement a demo program. In this video, we'll be looking at one of the more widely used reactive programming frameworks called reactive extensions, which is often shortened to ReactiveX or simply Rx. Rx is not part of a standard Python installation, so we'll need to use pip to install it. No problem, it's only a single command. If you prefer to install to your Python system library instead of user library, or you're working in a virtual environment created by the -- user from that command. Once we have Rx installed, we can move on to the fun stuff. Like our example in the previous video, Rx provides observer and observable classes, and they encompass the same basic functionality. The largest visible difference is that Rx's observable class has a large number of factory methods that can be used to construct special-purpose observables, especially observables that produce a sequence based on one or more other observable sequences. In other words, most of the operators and operations that we'll use to construct our reactive data flow are methods of the observable class. Let's take a moment to rewrite our demo from the previous video in Rx, and we'll see what that means in practice. The animal event class can stay the same, since it's just a data structure and doesn't know anything about who's using it for what. Our animal class changes quite a bit. The run coroutine method goes away, and in its place, we have a somewhat simpler generate event method. That name isn't significant, by the way. It's just a reasonable name I picked because it describes what the method does. The generate event method by itself doesn't encompass the entire functionality of the old run coroutine method, though. It knows how to emit an event, but it doesn't know how to wait a short while and do it again. That's where the asObservable method comes into play. That method uses one of the observable class's factory methods to create an observable sequence that's backed up by what is functionally a generator, although it's not implemented as one because that concept doesn't exist in every language that Rx is portable to. So instead of a real generator, we provide it with a state variable, which in this case is just the animal instance, along with functions it could call to check whether the sequence continue, update the state, get the next value of the sequence, and determine how long to wait before producing the next value. The factory method also accepts a scheduler object, which we'll come back to shortly. So what we're asking for here is an observable that produces animal events at random intervals from 0 to 10 seconds. Now the animal class may be a little simpler than it used to be, not a big difference. However, take a look at what happens with the sometimes loud and output classes. They're not classes anymore at all, just functions, and significantly simpler. The sometimes loud function takes an event and returns an event, and we'll use it to map from one observable sequence of events into a new one, just as you'd expect in a functional programming environment. The output function takes an event and returns none, which is again what we'd expect for a side effect in a functional system. So what do we need to do to put it all together? Well, first, we create an async IO scheduler, which is an Rx scheduler that specifically integrates with an async IO event loop. Rx contains quite a few different scheduler implementations that integrate with various event loops available in Python, as well as one that uses Python threads to implement scheduling. Regardless of which scheduler we use, the scheduler's job will be to decide when time-based elements of our event pipeline occur. That means, in this example, that the scheduler is going to be deciding when our animal observables produce new values. After creating the scheduler, we create the animal objects and their observable sequence of events. Now comes the interesting part, where we tell the computer how to combine and process those observable sequences. First, we merge the elephant and lion sequences into a single combined sequence and process that sequence through our sometimes loud function to create a new sequence we call louder. The select method used here is the direct equivalent of the map function in a functional programming environment. Next, we merge the louder sequence with the remaining animal sequences and tell the system that whenever a new value arrives at the front of that merged sequence, it should call the output function on that value. The doAction method used here is not equivalent to map because it doesn't transform the sequence, just performs an action on each element of it. The doAction method is for side effects. Finally, we subscribe to the completed event on the out observable sequence, which is the same as the sequence merging all event streams into one. Since the doAction operation returns its input sequence unchanged. When the sequence is complete, we set a result value on the done future. Since we used that future as the parameter to run until complete in our main.py file, setting its result value terminates the async IO event loop and our program ends. Our demo here has shown us the merge, select, and generate with relative time factory methods of observable. But that's just the tip of the iceberg. There are so many observable factories that it would take more time than we have just to give a short description of each one. Each of them gives us a useful way of constructing an observable, usually, but not always, based on one or more other observables. Python's interactive shell and help function are our friends here. There's a lot to be learned by poking around in the observable class. In the meantime, we're going to talk about a few of the very best observable factory methods that we haven't seen yet. First on that list is observable.create. This is the recommended way of creating a completely customized observable. The create method callable as its parameter and calls that callable each time an observer subscribes to the observable. Here, we've created an observable that says hi when an observer subscribes, and then never produces another value. Not the most useful of sequences, but it serves to illustrate the idea. We could take the basic framework and construct an observable with any behavior we like from it, without subclassing the observable class and without re-implementing, probably incorrectly, the internal machinery that keeps observables synchronized and functioning properly in an asynchronous or parallel environment. Next up is observable.selectMany, which is a more generalized version of select, where select applies a function to each member of the sequence to create a new sequence from the function return values. SelectMany expects a function that returns an observable sequence and concatenates those sequences. That means that the function applied by SelectMany can remove elements from the sequence by returning an empty sequence. And it can insert values by returning a sequence containing more than one element. As with select, the values added to the result aren't necessarily the same values that were passed to the function either. So, SelectMany can produce a sequence containing more or fewer values than the input sequence, and the values can be determined however we choose. Empty sequences and sequences of one value are easy to create using the empty and return value factory methods, respectively. Similarly, it's easy to construct an observable sequence of any already known series of objects using the of or from iterable factory methods. While we could use SelectMany to remove unwanted events from an observable sequence, it's easier to use the where method, which applies a callable to each element of the input observable sequence and returns an observable sequence containing only those elements for which the callable returned true. Now we've seen that fundamental ways to add and remove events observable sequences, so what about processing them? We could just use select and SelectMany to do all of our processing. But Rx provides us with min, max, average, count, distinct, group by, slice, sample, sum, and zip methods, just to name a few of the available tools. In this video, we looked at the reactive extensions for Python used them to re-implement our zoo demo, and looked at some of the broader possibilities of the framework. In the earlier videos of this section, we discussed what reactive programming is and implemented a bare-bones reactive framework to help us get a handle on the concepts. In the next section, we'll look at microservices, which are very small server processes that are meant to work together to create the desired result.